Yeah, Aaliyah's here. How here are you, Aaliyah? Can you talk back here, or are you just here with an ear here? Let's see, how do I share? Second camera. Yep, that's gonna work. And Daniel is here. How you doing, Daniel?
Pretty good. It's a bit early in the morning, but I'll survive.
Early in the morning, it's 11.
And
So if you were untroubled by the world, what would be your sleeping and waking hours, Daniel?
um probably sleep around 8 and up around 4ish
Up around 4.
p.m.
Sleep 8 to 4. Yep, you're right. This is 5 hours before your wake time. I will tell you that when I was in college, I had the same experience, and it seemed like I was falling asleep when I was trying to study, and then I'd lay in bed and couldn't go to sleep, etc. And one term, because your class schedule is, you're actually not in class that many hours. The majority of it is study. I just slept when I was tired. I didn't care when, where. If I was in the library and I couldn't stay awake, I wouldn't fight it. I'd just fall asleep. And then if I was in bed or it was time to go to bed and I wasn't tired, I'd just stay up and study. So I basically slept when I wanted to sleep. And short of class, I did not refuse myself sleep. And it was awesome. I only slept like 6 hours a day and I was always totally rested. It was awesome. If you could just figure a way to get life to revolve around that.
Yeah, there were last term there were a couple classes where I would actually, even going back all the way to the summer, there's some classes where I'd pull up Zoom on my phone and just attend from my bed because I couldn't be bothered to get out of bed for class.
Yeah, secret is to work for yourself and work from home. If you can pull that off and not have time. I told you guys I draw house plans on the side, and that work is really awesome in that regard because I really could do that. I could just, so maybe when I retire from teaching, I'll just go on my own sleep schedule. Cool. Awesome. We are going to talk about chapter 8 today, which deals with the concept of friction, which is the final concept before the test that you guys are going to take on Thursday. I don't know about you guys, but this feels like it's going fast. Seems like there's hardly time to process. So let's do that. So I had something, well, it wasn't funny to me, happened last year about the same time I was teaching this. And I'm going to propose it to you. The concept of friction. Actually, before I get into that, do you have any knowledge of that from your physics? I haven't taken physics in so long. I don't know exactly what you cover and in what detail. So
We covered it a bit, but it was like a year ago.
Say again, Daniel.
We covered it a bit, but that was like a year ago-ish, bit over.
Yeah. So here's what happened to me. I found myself laying on the floor in pain as a result of this problem. So I had this ladder set up in my garage. It was really short. It was only like 8 feet long. But the problem is it didn't have rubber feet on the bottom. It just was metal on metal because it was sort of half of a ladder, I guess you could say. So it was kind of aluminum on concrete, which is not doesn't have really a lot of friction. And so I'll draw myself over here and I'll use a stick person, not because I can't draw better than that. Okay, well, that is because I can't draw better than that. So I start climbing the ladder and everything is fine. Everything is fine. Everything is fine. Everything is fine. Everything is fine until I get like right there. And suddenly when I got there, what happened? You tell me.
The ladder dropped. Oh,
Yeah, so in a sense, what happened is the bottom of the ladder went that way. And of course, the top came down and I came down with it. My legs went between the ladder rungs and I got all like scratched a whole pelt of skin off the front of my leg, which was funny, except for being painful. But I'd like you quickly to try to explain why. Like my first instinct was like, that makes no sense at all. That makes no sense why that happened. So I want you to figure this out. So I'm sitting there and I weigh, we'll say 180 pounds. It's close enough. I weigh 180 pounds. And what bothered me, because I understand engineering a little bit, is this whole free body diagram. I was like, why would the ladder effectively want to go that way when the only force in this free body diagram, if you will, when the only force is vertical? So the ladder was aluminum. It didn't weigh very much, but even if it did, it kind of like took me plus the ladder. Now it's 182 or something like that. So in a sense, the ladder can be thought of as weightless. But it did not slide when I was lower. And it wasn't because I jumped when I got up there. It was when I got about 3/4 of the way up, then it slid out on the ground. And what as I said, what bothered me is like, why would it, where's the force coming that wants the bottom of the ladder to slide out when the only force here is going straight down? I'd like you to think about this a bit and, well, draw a free body diagram of that predicament. So again, we simply, let me do a little better than that. We simplify things a bit by thinking of things as particles. So there's me reduced to a center of mass at 180 pounds. And here we are on the floor. And I don't remember what the details of this were, but just for the sake of argument, I mean, I know that you want that relatively steep. And so let's say I had that set at, I don't know, 62 degrees or something like that from the ground. So there's the free body diagram. And I know the ladder was about 8 feet long. So let's just say it was 8 feet long. So the ladder itself was 8 feet long. So what I was thinking is, from the free body diagram perspective, is, well, of course the ground is going to have to push up at 180, but that was kind of all I was thinking. Like, obviously if I set this in the mud, then my weight on the ladder would cause it to sink into the mud. But it was like, that's the only two forces that I saw happening. So I just couldn't understand why this would produce horizontal force. So I want you to think about that for a second and see if you can make any headway.
Has to lean up against something to cancel out the torque from the weight of you.
Yeah, so there is definitely a force in A at Y required, because it was sitting on the ground. Because there's no way that's going to stay there. So as far as my free body diagram, I could clearly see why that would have to be there if I think of the ladder as kind of floating in midair. But I just thought, I'm done. Why does the ladder want to slide out? What's missing from this figure, from this discussion? Like, you tell me, like, can you, I just want to brainstorm with you about it and give you a chance to reason.
Well, I know there's going to be static friction on the ground opposing the ladder wanting to slide out. A horizontal force there.
But where is there any force? Like, why would there, there's nothing wanting it to go left and right. Where's that coming from?
Yeah. Does that have to do with the torque from the 180 pounds on the ladder? Does that work?
Yeah, that's exactly right. And you're onto it, Ben. If you just think in terms of force in X and force in Y, then as long as the force of AY is up to the challenge of 180, then we're done. Except for, yeah, you're not considering moment. And so if I threw in 180 down here, I'll erase that. But if I threw that in there, does it make sense? That does not account for torque. Like this thing is spinning, like it's not static right now. If this thing is in midair, it is not static right now. There's stuff missing from this picture. So let's think about that. What is the sum of the moments about point A? Well, remember, you got to decide, what are you going to do? So just to keep it simple, let's say that that I'm 6 feet up on the ladder, because notice we have to know where I am on the ladder now for this to work. So we have a distance of 6 feet, but the 180 is not going the right direction. So we either have to convert the distance or convert the pounds. In this case, I'm going to leave the pounds alone. Does it make sense if I extend this out? This length right here would be, I could say that the cosine. So if I called that L right there, I could say the cosine of 62 is equal to adjacent L over hypotenuse 6 feet. So that length right there then would be 6 times the cosine of 62 degrees, which my magic box says 6 cosine of 62. Whoa, what's happening here? Gotta get a fresh calculator. 6 cosine of 62 is 2.82.
Brian Johnson.
Approximately 2.82 feet. So now I can say, okay, I'll leave the 180 alone. Do you agree that the 180 is a perpendicular distance now of 2.82? So I can say, okay, it's 180 for a force times a distance of 2.82. I'm rounding that off, and that's feet and that's pounds. And so I'm okay with labels. Let's see, and that's causing clockwise rotation. So I guess that'd be negative. So this thing is spinning, right? So it's not static. Like, that's not equal to 0. I need this to be equal to 0. Where's the equal 0 coming from? Where are there forces that I haven't drawn into this picture that now apparently have to be there? Do you understand that? Chime in. You tell me.
Well,
do we need maybe to have moment in the opposite way?
You mean around B?
Hmm.
Yeah, I mean, we need moment. We need someone pushing it the other direction, because right now this is the only moment I can see. As I said before, notice you can think of force of AY down here as being 180, but it's pointing right at A, so it has no distance. So what's gonna kick this thing back in the other direction? Because right now this is not equal to 0, right? Which means even if I left the ladder there and stand on it, that thing is rotating. And you can stand on a ladder like that and doesn't rotate. So it's like, why? What's missing from my free body diagram? Take a look at the original
Wall.
picture over here. What's missing over here?
Is
The
that
wall.
force? Yeah, force BX.
Yeah, it's against the wall, right? That's exactly what's causing this. So if I come back over here, this is against the wall. There is a force at B in the X direction. And so that's the next part of this. Well, notice that would be causing positive rotation. Force at B in the X direction times a distance of, well, wouldn't that be the distance all the way up right there? So this distance over here. For similar reasons that we just did a second ago, that'd be 8 times the cosine of 62. Which my magic box says 8 times the cosine of 62. No, that's not true. That's the sine, because it's longer than that. I'm thinking, by the way, of the 62 being up here. So that'd be sine, not cosine. So 8 times the sine of 62, which is about 7.06. So now it's possible. So that's the key concept behind a free body diagram. You got to look at the ladder, but you got to take it away from everything and say it's floating in space. Well, you understand that. Like if you took a ladder and stuck it on the ground like this and it wasn't leaning against a wall, can you climb up it? No, because then it's just going to go thunk to the ground. As a matter of fact, you don't even have to climb up it because the ladder weighs something and it's just going to clunk to the ground. It's going to rotate in the clockwise direction and just fall to the ground. So it's got to be leaning against something. So you might say, well, duh. Yeah, well, that's because that wall has to push back. And we're seeing, because of your understanding of engineering, why that's happening right now. So notice I can solve for the force of B in X now. So if I take 180 times 2.82 and add it to the other side, 2.82, and then I divide by 7.06, divided by 06, I get 71.898 or 71.9 force of Bx equals 71.9 pounds. So now it won't rotate. So my free body diagram was missing something over there. Now it's in place. Notice, oh, because of moment, there has to be a horizontal force there. Well, now because there's a horizontal force, what keeps since that horizontal force exists, watch this carefully, what keeps the ladder from just sliding in this direction now? What keeps it from just sliding left? If it's now being pushed on by roughly 72 pounds, then how come it isn't just sliding to the left? My free body diagram is still missing something.
Yeah, we need to have the friction force from the floor to push back.
That's exactly right. Now it will do this. In other words, if you put a wheel on the bottom of that ladder and you climbed up it, it's gonna go. So now enter the fact that there's a force at A in the X direction. And really, we saw this the other day with that demo that I did where I put that stick on the wall and so forth. Remember how there was a force on it vertically, like it had to be there, or the thing was going to move? That's kind of true here too. If you put something on the ground like this, there's going to be a force vertically and horizontally. Now notice that that attachment point down there is nothing, like it just sits there. It acts like a roller joint, but it's not a roller in the sense that there's not a wheel on the bottom. That is not a frictionless connection. And that's what we're doing in chapter 8 is we're saying that's touching right there. There's going to be some friction right there. So if it wasn't for that friction right there, then that ladder is going to fall. Now, notice that's the only other force here. That's the only other horizontal force. So notice it's sort of automatic that, well, I guess I could write it out, although I don't really feel like I need to. The sum of the forces in X would have to be equal to force of AX pushing to the right minus force of BX pushing to the left. We just saw that that was 71.9. And of course, that always has to be equal to 0. So that's going to force, or that's going to cause the force of AX to also have to be 71.9 pounds. Again, I don't know if I needed to write out that equation to get that. Those are the only two horizontal arrows in this picture. So do you see that sort of the house of cards as a result of this? And so I don't know if it makes sense to you. It should, but watch this carefully. If I climb the ladder and I'm really low down here, does it make sense if I'm really low on the ladder that my 180 for this moment calculation up here, my 180 is going to get multiplied by a really short distance. So it's not going to create much moment. And if it doesn't create much moment, then the force of BX is going to be smaller. And if the force of BX is smaller, then the force of AX is smaller. But basically I got up there to the point where the force required for friction was up to say 72 pounds of force. And because it was aluminum on concrete, which is a really slippery kind of surface, it couldn't do it. Does that make sense? And then it slid out. That's what we're talking about today. And this also demonstrates, I think, why a free body diagram is so important. And it's sometimes hard to not to recognize, you know, all the arrows that belong there, if you will. So the point is now, even if, as far as attachment points, even if something is just resting against something, there's forces, both X and Y, even if it's not actually attached to the ground in any way. So this is the key concept today, force of friction right there. So I want to show you about that. Let's see. So demo, stop share, share something else, advanced second camera. I want you to watch something that you're familiar with. So I'd be demonstrating this in a little bit grander way if we were in class right now, but I obviously don't have any way to do this. Let me adjust the stand up a little bit. So I have this app on my phone. I'll go back out of this and show you what it is, but it's called Sea Level. It's kind of a cool app. I end up using this for all kinds of things. But if I go to Sea Level, this free app, let's see, there's all kinds of things it'll do. It acts like a level. It measures distances. It measures height. But I'm going to go to this thing called the clinometer, and I want you just to watch what it's doing. So I'm setting it on top of this book, and notice it's kind of reading the angle that I'm at. And I'll turn it this direction. Let's see here. Notice how when it's, let's see, can you guys see that okay? Make sure so you can read it. Is that right set up to you guys? I'm a little confused about what you see. It's a little more readable now than it usually is.
Yeah, it's
So,
right set up.
when this thing reads 90, it's actually flat. In other words, it reads 0 when I hold the phone straight up and down. In other words, when I hold it like that, see how it's trying to read 0 there because I'm holding it straight up and down. So that's what it calls 0. So I'm just laying this down right now. And so this is kind of cool because it tells us what angle we're at. Now I'm holding my thumb on this so that I can tilt the book and it doesn't fall. But now I'm going to stick this eraser on here. And this eraser has a, actually, I think I'll take this cover off. So you know what erasers are like. They're kind of rubbery in substance. And so notice I've tilted it up. See how it's reading like 80 degrees. So it's at a 10-degree angle. Do you understand? So you can't see that very well, but that's why I put that kilometer up there. So it's at 10 degrees. That thing is not sliding, right? And now I take it up to 70 degrees, which basically means it's at 20. You understand that? Like the book is angled at 20 degrees right now. And it still isn't sliding. Whereas maybe that pack next year, are these two going to slide at the same time? So the eraser has the advantage that it's rubbery and it's kind of sticky against the book. This is really slick. What else is different about these two things?
Weight.
Their weight. That's really important. The weight is really important too. So wake up, app. Come back, app. Oh, I hurt your feelings. There we go. So let's just look at the eraser and let's see how far we can tip this before the eraser actually starts to slide. We just need to get an approximate for a demo here, but maybe that, see how that other one started sliding? Why did it start sliding? Because it's slick against slick. Do you understand that? That's why my ladder tipped over. The eraser has not slid yet because it's really rubbery. So that's what friction coefficient's about. How frictiony is each surface? So I'm going to keep going until this thing slides. And I'm just staring at the number. You help me stare at it and tell me when it starts to slide. So it's at 50. Feels like it's about to go. 50. There it went. So let's say that was about 49. So that was at 41 degrees that it slid. Do you understand that? It slid at 41 degrees. So let's draw a picture of that. Draw a picture of that sideways. I'm going to get back to a screen where I can write now. Landon's here. Welcome, Landon.
Yeah, I accidentally uninstalled Zoom when I was trying to boot up today.
Sweet. So we said it finally slid at 41 degrees. I'd like you to draw a free body diagram of that eraser sitting there. So we had this plane and we said it was inclined at 41 degrees and we had this eraser sitting here on it. And at that point, it started to slide. And so that makes sense. That's something you've kind of felt before. You sort of understand that. But let's do one other thing now. So I guess because I already took this away, I won't show this to you live, but I have in front of me here, my friends, a scale. And I got this from a cop who absconded it from a druggie. So this is a drug scale. Used to live a life of crime, ruining people's lives, and now it is instructing engineering students. Isn't that glorious? So I stick this on here and it is reading grams right now, and it tells me that that weighs 30.5 grams. 30.5 gram eraser. So here's the key concepts that you need to understand. So how much does that eraser weigh? Somebody chime in on this. Why do I have to be really careful here? Just like we did the other day. 30.5 grams is not a weight. It's not a force. What do I have to do to it?
Multiply it by 9.81.
Multiply it by 9.81. What else do I have to do? Force equals
Convert it
mass
to-
times acceleration.
The kilos?
Yeah. So a Newton is a kilogram meter per second squared. So Daniel's 9.81 is the meter per second squared, and the mass has got to be in kilograms. So my weight is actually divided by 1,000, 0.0305. Is that right? 0.0305 kilograms. So I've got to take 0.0305 times 9.81, and then I get a 0.299. Tempted to call that 0.3 Newton force. So I had to convert that, which I think is kind of cool. Now, I want to do something we haven't had an occasion to do before, but I want you to think about this. I showed you this in one of the book's answers the other day. If I think of that axis right there as the x-axis, in other words, I think of it as horizontal, would you agree that part of the component of this is going into the table or into the book in my case, and part of it is down like that? Like that's what I actually have to convert that orange force into. I have to convert it into how much of it is going into the book and how much of it is going downhill. Now you can do that leaving this alone. But what I'm saying is it works better, at least it thinks more clearly, if you flip this thing sideways like this and you say, okay, I'm going to call this the x-axis and turn it so that it's flat. And if I do that, then maybe I'll switch. I can leave it alone, I guess. Then would you agree that that's really my 0.299 newtons? It's actually kind of going at an angle. You with me there? So maybe it's a little easier for you to see now that part of that wants to go down and part of that wants to go horizontal. And if I make a right triangle out of that down here, maybe that's the easiest place to see it. Now, where does the 41 go? You got to be really careful with this. Let's see, if that's 41, then this angle up here would be 49. So I could think of this as 49, which makes that angle 41. Is that right? You agree with that? So this angle up here is also 41. Got to be careful with that, right? You could get that wrong. So that means if I take the hypotenuse, which is 0.299, and I modify it by multiplying it by the cosine of 41, that'll give me the force straight into the ground, or straight into the book in my case, times the cosine of 41. I got 0.2256, so 0.226. And this over here would be the sine. If I take 0.299 multiplied by the sine of 41, and sine of 41, I get 0.196. So this is basically my force in X, and this is my force in Y. Everybody okay with that? So the point of today is my free body diagram is missing something. It's missing the same thing that my ladder free body diagram was missing a minute ago. And that is this. If I draw these back up into the picture above, so it's kind of, you know, oriented toward normal, then what I'm saying is the force in X was 0.196. Does it make sense part of that force wants the eraser to slide down the, I mean, if that's not zero, this is going downhill. Do you understand that? This thing is heading down the ramp. That's why things want to slide downhill, because the angle converts your force, which always stays vertical. I don't care what you do with the hill, the force is always going to go toward the center of the earth. But it converts part of that to horizontal and part of it to vertical. So what's going to stop that from sliding down the hill? The answer is nothing, unless there's, well, what's missing from this? Force of friction. That's missing from our free body diagram. You got to start adding that today. Does that make sense? There's always friction. Now you'll see problems where they say something is frictionless. By that they mean, it's too complicated, don't worry about it, or it's really tiny. You know, it's a tiny amount, so let's just ignore it. But now our free body diagram has everything in it that we need. And so does it make sense that in my case, the force of friction must have been 0.196, like just equal when I got it to that point? Does that make sense? Like when I was tilting it earlier, does it make sense when this is relatively flat and I start tipping it, it wants to slide down right now, doesn't it? It wants to, but the force of friction of the eraser against the book is bigger. In other words, force of F is larger than the force in X. So it won't go, but at some point it gets big enough, and then the force of X is big enough that it says, well, friction's not going to do it anymore. And now it's gone. So in our case, because we measured right at 41 degrees when it actually slid, we kind of had the point where it actually just changed. And so this is really powerful, what we just did. What you're going to see in all your book assignments is they're just going to tell you, oh, this cart has a force of friction of 0.2 or something like that. And you're like, where did they get that number? Well, I just did a demonstration where I'm going to show you how to actually get it. So here's what's really cool. 0.1, 0.226. So this force we figured out was 0.226 newtons. It turns out, and what Evold said earlier is really true. There's two things that affect whether something slides. One of them is what's the friction coefficient? Rubber on rubber is really frictiony, and it's not going to want to slide very easy. Aluminum on concrete, smooth concrete, not really low friction coefficient there. Like it's going to slide really quickly. And so the second part of it, though, is weight. If you have a lot of weight, and you can appreciate this from personal experience, if you have a box on the floor and you decide to push it, I'm going to push this box out of the way, and then you try to push it, and it's like, God, the thing won't move. Like you got to get down on the ground and really push. That's probably because it weighed a lot, right? You can appreciate that. If I have an empty cardboard box, you could just thump it with your finger and it'll slide across the floor. But then you put some dumbbells inside it, and all of a sudden it doesn't want to slide. So you can appreciate the weight is part of that too. And it turns out, and this is amazing, and this should be what you learned in physics before. It turns out that if you take that these are proportionate to each other. If you take the force of friction and you divide by the normal force, this force right here is called normal, which is sort of code for perpendicular. It's the force, the component of force that's going perpendicular to the hill. It turns out that that's a constant. The relationship between the force of friction and the normal force are constant when you divide them. So there's a proportion there. And this constant is called the friction coefficient. and it is often abbreviated with the Greek letter mu. So here's what you need to take away and what you're going to see if you kind of see this written in the book. Notice I could resolve that equation for force of friction, but I'm going to change it slightly. Instead of calling force of friction, I'm going to put an S there. And then I'll multiply the n to the other side. And then this is mu. I'm going to put a little s there too. The s is for static. So what we saw a second ago is the eraser was static, the eraser was static, and then it started sliding. And so it turns out, and we'll get to this later, but it turns out there's a difference between static and, so see how this eraser wants to stay here at the angle I have it at? See how it's not moving? And yet, if I put it on here with some motion, do you see how it sort of wants to slide? Like there's a difference between whether something is static or like it'll kind of stick longer. If I tilt it like this, it'll stick. And then it finally slides right there. Yet if I put it on here now, notice it slides super easily. There's a difference between kinetic friction, like friction in motion, and friction that's static. Anyway, that's not super important right now, but for now, this is the formula that you need, and you'll see it written this way. So a better way to understand it is what I said over here, which is the force due to friction is just proportionate to the normal force. In other words, it depends how much force is on the ground, how much of that is going into the ground. And by the way, I don't know if you noticed this, but the more I tilted the eraser, the less force it was actually putting straight into the book. When the book is flat, does it make sense? All of its, what was it, where did I write that down? All of its 30.5 grams were going straight down into the book. Does that make sense? But then I tilted it up. Now, how much of its weight was going down into the book? Well, not all of it anymore. It wasn't the same amount. If I take 30.5 times, or 0.0305 times 9.81. Yeah, that 2.99 we had earlier, that 2.99 right there. Notice only 0.226 of it was actually going into the book. So the more you tilt something, the less force is actually heading into the book. And so that's also part of what made it slide. You see what I'm saying? Like some of its weight, keeping it from wanting to slide, is going to waste. So in our case then, this is really cool. We actually found mu of s. Now, how did we find it? What do you mean we found it? Well, for that thing not to slide, the point at which it slid, it had 196 newtons of force going this way, and its force of static friction was going that direction. And we had this force going normal to the hill of 0.226 newtons. So does it make sense right when it slid? Right when it slid, force of static friction was equal to 0.196. Does that make sense? That's the point where they were equal. And based on that formula I just told you above, that's the same thing as the normal force, which we found out was I'll write it in here, normal times mu of s, but we found out the normal force because of our free body diagram was 0.226 newtons. And so all I have to do to figure out the force of static friction is just divide both of them away. And I want you to pay attention to units here. What are the units of this friction coefficient if I take 0.196 newtons and divide by 0.226 newtons? What are the units?
It's unitless.
Unitless. I got approximately 0.87 for that. unitless. Think of this as like a percent. So in a sense, what you're going to get for these static friction numbers is numbers between, I'll say percent, between 0 and 100%. So if you have a mu of like 0.8, this is like high friction, like rubber and asphalt. That's why car tires are rubber. Like we don't want those sliding off the road when you turn sideways. We don't have metal tires on concrete. Like that's not good. You're going to slide off the road. A mu that was really small, like 0.12 or something like this, really low friction. Slides easily, in other words. Does that make sense? Now, for all your book problems, they're just going to give you a number. All right, let's just try out a couple examples. Let's see. Let's do one more cool example. Did I already download this? I can't remember. Nope. So I think I've told you guys I'm in Ski Patrol. So I took this slide directly from a training that I had to take because one of our main jobs in Ski Patrol is to put somebody injured in the sled like this that's jacked up, like they can't ski anymore, whatever's wrong with them. And we got to somehow get them down the hill. But what's keeping that from sliding down the hill? What's keeping that? So I'm the skier there. I weigh 200 pounds. And there's this person in the sled. Between the person and the sled itself, they weigh 300 pounds. Because it's on a hill, does it make sense there's a component of this that wants it to go downhill? I mean, my question to you is how badly does that want to go downhill? Given that that's effectively 200 pounds and 500 pounds. Let's do the same thing we just did a second ago. Just to keep it simple. Again, I'm going to consider this right here to be the x-axis. I'm going to rotate the axis so that I can think of it as flat. And so what I really have here then is this 500-pound weight, me and the sled combined, this 500-pound weight that's at an angle. And since that is 20 degrees, I'm going to draw this a little more accurately. Then this angle here is also 20 degrees. That's where the 20 degrees goes. So I have these two forces. Since 500 is really the hypotenuse of this right triangle, then this normal force over here, or you could say the force in y. But again, that's the way. Actually, I don't know if I'll even say that. This is the force in the y direction. Normal and the force in y are the same thing. I'm going to get that by taking 500 times the cosine of 20. I get 460. I'm just going to round it off, 470 pounds. So because that's not a very steep hill, most of that 500 pounds is going straight into the hill. But some of that is going downhill. And that'd be the force in Y. I'm sorry, the force in X. Which would be 500 times the sine of 20 degrees. Much smaller number, 500 sine of 20. 171. Maybe you're surprised. Maybe you're surprised that number is so big. Do you understand what that's doing here? Again, we're doing what we've done the entire term, which is taking a force at an angle, and then we're breaking it into its component parts, into its X and into its Y. Do you understand that collectively this is going into the hill at 470 pounds, collectively, all of it put together, but 171 pounds want this to go downhill? Does it make sense? Like, that's not good. How is that going to get stopped in this picture? What's going to stop that 171 pound force?
Friction. Coefficient
That
of friction.
right there. Maybe you've never skied before, but you need sharp edges on skis. If I can dig the sides of my skis into the hill strongly enough to create enough friction, then I might be able to stop this 500 pound weight that, because of the hill, is 171 pound desire to go down the hill. So let's consider this for a second. So I told you a second ago that friction coefficient, if it's small, if it's small, that means it's pretty slippery. Does that make sense? Now that's not really small, but it's reasonably small. If I told you that was the friction coefficient between my skis and the hill, would this stop? Would this stop the skier? Would this stop the skier and the person in the sled? Well, this is where the formula that I just told you comes into play. The force due to friction, sometimes called F of S. In this case, I'll just write it really simple. This formula comes into play. How much force is there due to friction? Case number 1. How much force is there due to friction? Well, friction force is equal to the normal force. Hey, we just calculated that, 470, multiplied by the friction coefficient, 0.3. Notice again that friction coefficient is unitless, so this is 470 pounds times 0.3. I get 141 pounds. What does that mean?
Well, if you're not doing anything else to slow yourself down, you're going to be slowly accelerating as you make your way down the hill.
Exactly. Notice there's 31 more pounds sending me, 30 pounds more sending me downhill. Now notice that's not huge, but I'm not stopping. Like if I want to stop, I'm not stopping unless I can create more friction somehow, or lose weight, dump the skier, dump the passenger, the patient who's already injured, like kick him out of the sled or something like that. Like I got to get the weight to go down. So this isn't catastrophic, but because it's only 30 pounds over, but I can't stop. And I've been in that circumstance. One time I had a person in my sled and I was like, this is a pretty low slope and I'm not going that far, but the person was really huge and we started flying. Like I could not stop them. And so I just tried not to crash because I'm the steering wheel. And if I lose them, then they go flying into the trees. And then I've got to run and pretend I was never there. So the only thing I have control of is just tilt my skis more. Does that make sense? If I tilt my skis more, But the other thing I'd like you to notice is I'm oversimplifying this a little bit because the only weight that's applying to friction here is just me. Like it's only 200 pounds that's on the skis. Do you see what I'm saying? So I'm oversimplifying this. It's actually a little worse than what I'm showing you because all 500 pounds does not act together. The 300 pounder is just adding his own weight going down the hill. So it's really the 200 pounds that I have to convert to do this. And so this is worse than what I'm drawing. Do you understand that? But I just don't want to overcomplicate it for the first problem that I'm giving you. Well, let's consider the second case. You can see that I'm fairly close. So what if I tilted the skis a little bit more and got it up to 0.4? Well, then let's see what happens then. Is that enough? What's the force of friction now? Well, 470 times 0.4. What do I get? 470 times 0.4. I get 188. Awesome. So this one is moving. This one actually stops. So the thing about force of friction is you got to think of it as being something that's available. It's not something that you're using. In other words, it isn't going to drag you up the hill. Does that make sense? If you get on a flatter hill, it's not like, oh, 188. Well, that means if I'm on a flat hill, then I'll just start flying that direction. The force of friction is kind of a resisting force. Does that make sense? And if you get more force against it, then it's going to give up and start sliding. That's what happened with the book and the eraser. Right now, the friction is enough. It's still enough. That's why it's not moving. But at some point, it overtops it, and then it starts to slide. And now it's not enough anymore. But it's not like when it's sitting here, I put it here, and it goes zing and flies uphill. So I guess you could say in our case, if the force of friction is greater than the force in the x direction, then it won't slide. Notice the force of friction is always in the opposite direction of travel. In other words, the hill wants me to slide down. The force of friction is stopping that from happening. Does that make sense? So it's kind of cool. Both of these numbers, this is the big takeaway, I think, for today. It's like we took this 500 pounds and we had to convert it into its X and Y components. And both of those together played into whether this was going to slide downhill or not. We needed the 470 and the 171. Let's see, what is this? Oh, that's an awesome problem. I got to do that too. So let's consider this mountain biking problem. This is a big, beautiful question. So a huge part of mountain biking is, can you control your speed? Like, are you on a hill that's so steep you can't stop? This last weekend, when I was down in Santa Cruz, we went down this section of the trail called the Waterfall, and it was so steep you could not stop. Like, you had to keep rolling and, turn over rocks. And if you tried to stop, like, you would go over the handlebars, and it's cool. So let's take this from scratch. And so, you can visualize this as a car, going down a hill and all kinds of cool things. But let's do some cool stuff with this. So what does that G represent up there? I mean, you're going to see a problem like this on the test. So, because this is such a cool problem. Why did I call that G as opposed to A or C or N or some other letter? I know I'm asking you to read my mind. That's, well, gravity, center of mass, center of gravity. So, you know, calling it center of mass would probably be clear. But in other words, I'm saying between the bike and the person, that's where the center of mass would be, somewhere up in there. And I gave you dimensions to it. And we're saying that total, the bike and the person weigh together 210 pounds. So what we want to know is this going to slide downhill, and you know, what's going on? Can you appreciate if you have knobby tires, which you have on mountain bikes that want to dig into the dirt? That'll help. That'll increase the friction coefficient. Well, let's figure everything out about this. And I want you to go as slow as you can here and ask questions. So does it make sense that I got to do what I did before? So I'm thinking of this as, again, the x-axis. I'm rotating the axis, which we've never done before. And in my case, like I can turn what I'm writing, but it doesn't turn what you see. So in a sense, that doesn't help. But there's these two components that I need. One of them is going perpendicular to the hill, and one of them is going parallel to the hill. The one that's going parallel to the hill, again, determines, does this want to go downhill? The one going into the hill is going to determine how much effect the friction has. And so I got to convert those. Like before, this angle up here, through a little bit of geometric thinking, is going to be 32 degrees again. So I'm going to call this the force in Y, and this is the force in X, since I called that the x-axis. And I know that those are the direction they're pointing. Does it make sense? I'm just using logic to know which direction those point. So wouldn't the force of, as we did a minute ago, 210, if I want the force of Y, if I take 210 pounds times modified by the cosine of 32, that'd be the force in Y, which is approximately 210 cosine of 32. It's approximately 178. So part of my 210 pounds is going into the hill. And I like that, because if I have a lot of weight going into the hill, then that'll mean my friction is more useful to me and I won't slide. Do you understand that? So lots of it is going into the hill. That's really good. Well, what about the force in Y? What's the force in Y? Well, that'd be 210 times the sine of 32. So did I just say Y? I meant X. So 210 sine of 32, that'd be 111. I'm just rounding these off so it's easy. Again, that's a fairly fair amount. That's like more than half my weight. So this wants me to roll. I love gravity sports, and so I'm all about being on an angle in skis and a kayak and a mountain bike. This is fun, like gravity. So that's what the force of X is a desire to roll downhill. The 178 is effectively helping me stop. Now, one of the big takeaways for this, one of the things we've got to calculate here is, does it make sense that I'm touching the ground at A and at B? So I'm not oversimplifying this like I did just a minute ago. I'm going to consider A and B. Do you think the same weight, since I'm 210 pounds, do you think there's 105 here and 105 here pushing up? No. If you have a beam like this and the 210 pounds was perfectly in the center, then yeah, it'd be 105 and 105, right? But if I take that 210 and scoot it over to here, now it's not 105 and 105. And that's what's happening in my case, right? That 210 is not in the center. Well, and not only that, the 210 is at a weird angle. It's really the 178 that I'm worried about here. Do you understand that? So how do we figure out, and this is the language of engineering, the reactions at A and B? A truss sitting on the roof of a house. The truss weighs 5,000 pounds. Well, what are the reactions on the part of the house that the truss touches? Reactions at A and B. And this is where your free body diagram comes in. And we get at that most easily by moment calculations. So I'm going to call these the force at A in the Y direction, pushing back up, and the force at B in the Y direction, pushing back up. Do you agree that we're only looking at the force Y here? 210 is not what's pushing into the hill. That's why normal force is a thing. That's why somebody came up with a name for this. The 210 pounds is not a good way to do this. We want to convert it to 178. And now let's figure out, I don't know, the moment around, say, point A. What's the moment around A? Well, I've got force of B in the Y direction, a distance of 5 feet from A. And notice those are perpendicular. Again, I'm thinking of the ground is horizontal right here. So those really are at 90 degrees. So I didn't even have to change that. They're both what they are. And that's positive. Do you agree with that? That force is pushing and it wants it to rotate that way. We call that positive. And then we've got that 178. How far is it away from A? Somebody blurted out. Notice there's 90. How far is it away from A?
3.
Yeah, 3. You got 2 feet up there and 5 feet right there. So it's a total of 3 feet. That's all the forces, or that's all the moments. And we need that to be 0. Except for it isn't all of them. What's missing?
The force in X.
Isn't the force in X also a distance from A? Is that causing negative or positive rotation?
Positive?
Yeah, it's causing positive rotation. It's wanting it to rotate this way. So that's positive. So we got the force in X, which is 111. And isn't it a distance of 4 away, perpendicular? Now we got all of them.
Do we have to worry about the friction force at B at all?
No, the reason is, and that is missing from our diagram right now, but I'll include it now because you said it. That's the force of friction at B. How far is that away from A? It's pointing right at A, so it's at a distance of 0.
Yeah.
And this would be the force of friction at A. And notice I put them the opposite of the direction the bike wants to go. So this allows me, let's see, if I add 178 times 3 to the other side, and if I subtract 111 times 4 to the other side, and I divide by 5, I get 18. Notice of the 178 pounds going into the ground, only 18 of it is on the back tire. That is really light. What this means is this bike is really close to tipping over. Going over the handlebars is a big part of mountain biking. If that number had been 0, then we'd be balancing on our front tire. If that number had been negative, then we are going over the top. Do you understand that? It's very important. So of the 178 pounds going directly into the hill, only 18 of it is on the back tire. Notice I could actually switch now to the sum of the forces in Y. So I know I have negative 178 going down. I just found out that I have 18 going up. And I also have the force of AY going up. So the force of AY is the remaining 160 pounds of the 178. You could do the sum of the moments around B if you wanted to and get the same answer. That's amazing. So 160 pounds are on this tire and only 18 pounds are on that tire. Now, part of you should say, yeah, that makes sense, because isn't that you're up at a hill? Isn't more of your weight over the front tire than the back tire? That makes sense. So this is a very important point I want you to make sure you make note of. If this is negative, we're going over the handlebars. It's just kind of a cool observation to make. And we're close to that. Now that we know this, does it make sense? And notice we now realize, sweet, I'm not going over the handlebars. Like, I'm riding downhill, everything's fine, I'm having a good time. If I don't have the brakes on, does it make sense there is no force of friction because I'm just rolling? But what if I have the brakes locked up? Okay, now let's do that. Please interrupt, because this is such a neat example and I really want you to get it. Now let's lock the brakes. And let's say we have, and this is the way your book questions will be worded, let's say that we have a friction coefficient of 0.55. So that's the friction coefficient between the dirt and the tires. And as I said before, there's all kinds of interesting considerations there. Like if it's really muddy out, I've crashed a lot of times because I got onto a section of the trail where it was really muddy and there was no friction coefficient. In other words, you try to stop, you don't stop at all because it's just slick on slick, right? I've been in other places where the dirt was wet, but not and just sticky, and I had nice new tires, and like I could stop on stuff that was super steep. So what I want to know is, will I stop? I'm going to give you a second to think about that. Will I stop in this case if I lock the brakes up? Do you understand that the answer to that question is yes, if the force of friction at A plus the force of friction at B is bigger than what number?
111 pounds.
Yeah, 111. Isn't 111 how badly the hill wants me to go down? And so if those two friction forces added together are bigger than 111, then I will. Well, let's go figure out what those are. From the formula that I showed you today, if you take, since this number is equal to its normal force times 0.55, and this normal force times 0.55, and let's replace those. This normal force at A was 160, and this normal force was at 18. So 160 times 0.55 is 88, and 18 times 0.55 is 9.9, for a total of 97.9. So the answer is, will it stop? No. Do you understand that? Friction was only able to produce 98 pounds of stopping power, but unfortunately gravity wanted me to go down at 111. Now, again, I'm not flying out of control. This isn't a lot different. It was close to stopping me. Does that make sense? Now, you may have noticed as a shortcut, did I actually need to break those two forces up here into 160 and 18? Couldn't I have just taken 178 times 0.55 and answered that question? The answer is yeah, you could have. So if the only question was just, are you going to stop? Well, I could have stopped at 178 and said times 0.55 and see if it's bigger than 111 and I'm done. But it's kind of cool. And the reason I broke it into parts and kind of showed you, the reason the sum of the moments being zero and what equilibrium is all about is because that force on the back tire, the fact that the ground was having to push back means the tire was pushing down at 18 pounds, which means it was still on the ground. Do you understand that? So this is kind of cool. Like, I totally understand what's happening to this bike now. It's not tipping over and it's not stopping, even with the brakes fully engaged. How's your brain? Now, before we get off, the only thing that worries me about taking a test over this on Thursday is we really haven't had a chance to talk about it. I'd love it if you had a chance to ask me questions or something. I know some of you have a class after, but you know what I'd love to do in a sense is, I don't know, maybe this would work. Thursday, if I show up to class as per normal and you show up to class because you have a couple of questions from the assignment or from the review that I put online for you to look at, then you have a chance to ask me some questions and then you just start the test after you ask those questions. If you don't have questions, then you could just start the test. But what I don't want is just to say, okay, I showed you, goodbye. And it's one thing to, watch a couple problems, but it's another thing to be like, yeah, I actually can do this. And I certainly want you to be able to do that. And I'm, if you will, warning you in advance that I like this bike question. I think it's awesome that you can figure out these normal forces. And given that, we don't have near as much time between what I just showed you and the test, I'm going to put a question like this one on the test. And so maybe that helps you. Do you understand that, you know, another name, like I could have called this the normal force at A, and I could have called this the normal force at B. I mean, that's just another way to name it. So when you hear that, that's just language for, oh yeah, that force is actually, you know, perpendicular to the ground, because that's the one that matters. That's the one that matters in terms of friction. If that force was at some angle, then you can't just multiply it by the friction coefficient. It's got to be perpendicular. So normal to the ground is a big concept. If the ground tilts up at an angle, then that isn't so straightforward anymore. So the other thing is you got the rest of today, you got tomorrow, and you can hit me up. As I've said before, send me a text with respect to the review that I put in my open math for you, and you'd be crazy to take the test Thursday and not look at that first. But send me a text and say, hey, can we get together for a quick Zoom about, you know, some question either on your homework assignment or on the review. As far as the test goes, you want to pay more attention to the review than to the homework. But again, you'd be crazy to wait for the homework until Sunday, because you need to know that so that you can do well in the test. So I would encourage you to, you know, wade right into that right away. And the good thing is if you get that all done, then Thursday comes, you take the test, and you're kind of done with this class for, you know, a few days. You don't have to think about it. And I have another example I'd like to do, but I guess I don't have time. So, so I'm gonna put the test. I'm gonna put the test in to show up at 11. So you'll be able to open it at 11 in my open math, and ideally, again, print it off, because I'll have figures on there that you'd like to be able to use, kind of like we did here. It'd be nice to be able to draw on them and so forth. So print that off, write all over it, and then scan it and send it back to me, either email or inside my open math, but email is fine. You can just email it to me. There's only like 5 of you, so. How we doing? Are you okay? Like, I don't know. I haven't done the assignment yet. I don't know if I'm okay. All right, get yourself out of here if you need to. Feel free to stay after if you do have a second. I might at least draw a couple pictures on the last example that I was going to do in class that we ran out of time for. This is more of a book assignment question, kind of thing you'd see in a book, and it's actually a pretty good problem. I like it. I like it because it's somewhat realistic, and I like it because it isn't on a hill. Like, that helps. Like, what's causing this cart to want to go down the tracks is the fact that it's hooked to a motor that's like pulling it down the track. So this is like an iron ore car. It's like a train car, if you will. And so notice its mass is 6. What is that? M, capital M, G. What is that?
Megagrams?
Megagrams, which is millions of grams. And so you got to say, oh, that's actually 6,000 kilograms, which then I have to multiply by 9.81 to turn it into a force. So this isn't as nice as the bike problem where the forces were already in pounds and we were done. It's got to be kilograms, and it's got to be multiplied by acceleration, mass times acceleration, to become a force. So that's G. In other words, here's G, the center of mass of that cart. There's a force going down right there. And then there's this 10 kilonewton force. Notice kilonewtons, and that's already in newtons. And so that's already a force. Awesome. But my example over here is going to put this in newtons, and that's in kilonewtons. And so you got to make sure those units are the same. So then they tell us if the coefficient of static friction between the wheels and the tracks is 0.4, notice it says mu s for static coefficient of friction, and the wheels are locked. So it's like my bike. Let's lock this thing up, see if we can get it to stop. Find the normal force acting on the front wheels at B and the rear wheels at A when the brakes at both A and B are locked. And then they ask the question, just like I did on the bike, does the car move? So the main thing is that you understand that there's forces missing here. I've got this force coming down. I've got this force, which I was given, but then I've also got, notice it's pulling to the left. Therefore, the force of static friction, force of, I'll just say friction at A is going to be going to the right, and the force at B is also going to be going to the right, force of friction at B. So now my free body diagram is complete. In my case, I feel like out of laziness, I don't know if I need to redraw this. I got all the information over there in that picture that I need. Notice the center of mass is not in the middle of the cart because the whole cart between the wheels is 1.5, and it'd be 0.75 to the center of mass if it was, and it's not. So just like the bike a minute ago, the first thing you're going to have to do is come up with the reactions at those two wheels based on the sum of the moments around A or B, so that you know what those amounts are. In this particular case, because they said all the wheels are locked up, maybe I wouldn't have to do that. Maybe I could just take G and multiply by the force of friction. But it's kind of cool to find both of those separately using the sum of the moments. So I could, again, do something like the sum of the moments around A needs to be 0. The sum of the moments around B needs to be 0. Maybe I label this the normal force at B. Maybe I label this the normal force at A. That's the kind of thing you would see. So it's still just a force. So let's see, I'm just going to start into this a little bit since we're just hanging out here. I wonder what the sum of the moments in A would be. Well, I need it to be 0. So what is my moments? Let's go around B. One of the reasons I find myself wanting to go around B is I see the car pulling on the front. And one of the possibilities is it pulls and the front brakes are so strong that the thing lifts up in the air in the back. That's why I kind of find myself wanting to go around B. So I say, okay, well, I got a force of 10 kilonewtons. So I think I'll leave it at 10. How far is it from B? Notice it's 0.9 plus the radius of the wheel over here, 0.15, and those are both meters. So that's 1.05 meters. And that wants it to rotate in this direction, which is positive. So, okay, that's good. That's positive. So then I got this gravity force here, which, as we said, is 6,000 kilograms times 9.81 meters per second squared, which gives me 58,860 newtons. Since I decided to work, though, in kilonewtons, then I guess that force would be 58.86 kilonewtons. So I just decided to work in kilonewtons. Those are smaller numbers, easier to work with. Notice that's causing rotation that wants to go negative. So this would be minus a force of 58.86 kilonewtons times, how far is that away? Well, it's 0.6 away. Am I done? Are there any other forces? I've got 1, 2, 3, 4, 5, 6 different arrows. My free body diagram has 6 different forces on it. Are they all accounted for? Do you agree that both of these don't count because they're both pointing at B, so there's no distance. And then this force of friction over here is also lined up with B, so it isn't producing anything. But this this normal over here is. And that's also causing positive rotation. So I got to add that to this problem. So plus the normal force at B times its distance, which is 1.5 meters. And all of that has got to add to 0. I love that equation because it's only got one unknown. So now I'm going to know what the normal force at, I'm sorry, that was the normal force at A. I wrote B for some reason. Normal force at A. So if I add 58.86 times 6 times 0.6 to the other side, 58.86 times 0.6, and I subtract 10 times 1.5 to the other side, and then I divide by 1.5 meters, I get the normal force at A is 13.544 kilonewtons. As before, does it make sense I could switch now to the sum of the forces in Y and not have to do another moment calculation? Since all these forces are vertical and horizontal, I've got negative 58.86 going down. I just found out I have normal force of A, which is 13.544 going up in Y. And I've also got the normal of B. That's a much easier way to get the normal of B. But again, I would encourage you when you're just learning this, redo a moment calculation around A. You're going to get the same answer as we're getting here. You end up with 45.316. Why is it so much bigger? That should bother you a little bit. I know that 58.86 is not in the middle of the cart, but it's pretty close. So how come normal of B is, how come the front wheel's having to work so much harder?
It has to do with like where the 10 kilonewtons is located. How hard that's pulling out.
Yeah, it has to do with the 10. It's not so much where it's located, but let's pretend for a second, as I said a minute ago, let's pretend for a second that the cart just stops and you still pull on it with 10. What's going to happen to the cart? What's going to happen if I pull this cart from the top here and it's actually skidding? Isn't it going to lift up in the ground, up in the air? Well, that's what's causing it. The back tire is being lifted right now, and that's why it isn't having to work that hard in the back. So it's not what it would have appeared. I would have thought, you know, maybe 60% of that 58, 60% of it would have been here because it's a little closer to that side. But it's way more than that because of that pull, trying to tip it up in the air. That's why these moment calculations are so cool. Now, again, out of laziness, I would not have had to split this up into two parts because they never asked me that. They just said, if the coefficient of static friction between the wheels and the tracks is 0.4. Remember, collectively, NA and NB added together are still 58.86. Does that make sense? So I could now say that I guess I'll finish this since some of you are still here, but the force of friction at B times 0.4 plus the force of friction at A times 0.4. I want to check and see, is that greater than, well, the force that's actually trying to get this to go down the tracks? Is it greater than 10 kilonewtons? Those are the only horizontal forces, right? So does it make sense? I could have just said force of I could sort of factor out, if you will, the 0.4 question mark. I could have factored out the 0.4 and I already know, even before I did those other calculations, I already know that that total right there is 58.86. Does that make sense? I wouldn't even have had to split this up into two parts. What is 58.86? Clear 58.86 times 0.4. That's 3.544. That is not greater than 10. So hence it's skidding or sliding or whatever you want to say. It may be locked up, but it's still dragging it down the tracks.
I got 23.544 for that.
Yeah, I feel like something's wrong. Maybe, yeah. Oh yeah. I was gonna I said 58.86, but my calculator that 5 didn't show up. So I'm glad you said that. Yeah, 23.54. 23.54. So that's a different conclusion. And since it's kind of good that I found that. So the opposite is now true, right? Stops. The brakes were enough. Stopped. Good. My bike didn't stop, slid down the hill. Notice in this problem, they did tell us, we didn't look back to see this. They asked us to find the normal force acting on the front wheels at B and the rear wheel at A. In other words, they asked us to do both, but does it make sense we didn't have to actually answer the question? If the only question was, does the car move? We didn't have to find both of those separately, but I just think it's cool that we did. So this does stop, and the normal force at A is positive. Hence, the car isn't tipping. You understand what I mean by that? It isn't tipping that thing up. Remember one of Newton's laws, equal and opposite reactions. If NA is pushing up, if it's pushing up right there at 13 kilonewtons, then that means the car is also pushing down right there. So the car, there's still weight back there. Does that make sense? So we don't have time to get into all that. I just think it's so cool that you can actually understand what's happening here and how friction works and so forth. All right, I'm glad you guys are able to stay. I'm sorry this class always goes long, but you just need lots of examples to understand this. I think that one will help you get the book questions right. So.
All right.
All right.
Thank you.
We really should get out of here. We went way too long.